In 8.4, the idea was that we could take a binomial, right, and divide it into a longer or larger polynomial by using that concept of synthetic division. And we talked about the number that goes on the outside of the table being the opposite of kind of what you're dividing by. So if you were dividing by x plus 2, you put a negative 2 on the outside. If we're dividing by x minus 2, you put a positive 2 on the outside. So the technique, right, was important, the technique. So we're going to utilize that today to talk about what's called the factor and remainder theorem. Let's jump right into this. So let's do this first example. So what I want you to do to start for part A is just find f of 3. Just go with this old school stuff, nothing new here. Just go ahead and find f of 3 in the first part. When you finish the first part, go on to the second part and do exactly what we did yesterday, but this time specifically telling you to divide by x plus 3 in this case. Direct variation quiz, or direct and indirect variation quiz. Again, you have another quiz tomorrow. Tomorrow's quiz is going to 8.3 and 8.4. You really look up when you hear tomorrow, because you need this anymore.
I used to.
You have, okay, you got used to it, man? Because every time I say tomorrow, I feel like I'm saying tomorrow. Like, give that tomorrow. So I think I should get, let's see, I have this written down, 56. Is that right for part A? 56? Yeah. So you should have gone for part A, 56. Okay, just be careful if you're squaring, right? Squaring things with the negative signs and such. Now, part B we're going to do together because I know 2 people were out yesterday. So if they want to see what we did yesterday real quick, this is what we did yesterday, Sebastian, right? For part B, I'm going to do. So for part A, you have to be able to do it yourself. I'm not going to go through that. Okay, f of 3 turns out to be 56. Just plug in the number 3 in those spots. For part B, though, what I want to do is what we did yesterday. So what we did yesterday was to recognize when we're dividing by x minus some number, we take that number and it goes out front. This is one of those like small rules that I do want you to think about and memorize. Now when you divide by something, again, you're doing the opposite of what you see here. Kind of like the vertex form for parabolas with h and k. Sometimes you did the opposite, sometimes you did the same for shifting.
Wait, in this instance, you would divide it by 3. You would have 3 there.
Correct, because we're dividing by, look at part B what it says. Divide by x minus 3. Remember yesterday in class, when you divided by x minus 2, didn't we put a 2 out here? Go back and look at your notes again. Okay, in the homework last night, you should have done this. When you divide by something that has an x minus 5 or x minus 2, that 5 or that 2 goes outside. What goes along the top? What goes along the top, Isabella?
The coefficients for each of the numbers, variables in the equation.
Polynomial?
Yeah.
Function or polynomial, that works. So we're taking this function or polynomial here, or this expression we could even say, we're putting the coefficients. So I have a 3x cubed, I've got a negative 2x squared, a negative 4x, and a positive 5. Do I need zeros along the top anywhere? I see a lot of people shaking their head no. How come I don't need zeros here? Alex?
Because they go in order descending.
Yeah, look at the descending values. Cubic, squared, linear, constant. I'm not missing any powers along the way. If I were missing the x squared term, I would have to put a 0 in the place for the x squared term. I always start with my highest degree and work my way down from there. Now, The first step for all of these problems is to take the first thing and just bring it down. Okay? Don't let this confuse you. This is not used here every time. This is used here every time. They both happen to be threes. Again, it's a coincidence. Don't let it confuse you. This number is not going to be the same as this number. It's just a coincidence. It's these that are always the same. What do I do next? More? Did you watch the video?
What?
Do you want to read the notes? Watch the video?
Yeah.
Good. All right, what do I do next? Go ahead.
You multiply by 3 and then add to -2.
And then where does that answer go?
Down.
Right here. So again, multiply like this distribution, add to the next. Multiply these, add to the next. Multiply these numbers, add to the next. It's the same process. So 3 by 3 is 9. 9 plus -2 is 7. So the 7 goes in this place right here. Then I do the same thing again. I multiply these two and add the next one. So I get here 21 plus a -4 is 17. And then finally, 3 times 17 is? Plus 5 is? Coincidence? No, not this time, right? Not this time. Look at these numbers. Look at that. Look at that. It's incredible, isn't it? Incredible. Can anybody make a connection? Make a connection as to what we're going to go to, or what we're going to use this for, or where this is going to show up? You made anything
Because the C value was 3 and you had us find f of 3.
Interesting, right? So when I plug a 3 in here for x, what comes out is a 56 for y. So earlier, what have we been calling this the whole time? What's the word we've been using? Remainder. So what else can I actually call it technically if I want to? You know, this is kind of weird, but again, I put a 3 in for x, and what comes out as y is 56, right? So if 56 is y,
The remainder is y.
yeah, the remainder is really the y coordinate. Now, this is kind of weird. 3 is the x coordinate. Stay with me again. If I want to do direct evaluation with what's called direct substitution evaluation, I plug in 3, I get out 56. Is that clear that this is a coordinate? It's the same coordinate. Plug in a 3, what comes out is 56. So this is also called synthetic substitution. We called it synthetic division yesterday. But if I want to figure out, like, you know what, I don't want to plug in f of 2 and f of 7 and f of 8 every time into there, I can just put the numbers here. And whatever comes out as the remainder is the y. So the coordinate here is 3, 56. And that's either by determining it from A, direct substitution, or B, synthetic substitution. So again, it turns out that this is the x and this is the y. Write yourself a note, a little arrow. This is like plugging in x equals 3, and this is what comes out as y. Now, we've already made these conclusions, but let's see who remembers. What happens when the remainder is 0? What happens, Helen, when the remainder is 0? Yeah. If this were 0, it means that x minus 3 divides evenly into this function, which means that x minus 3 is a factor, isn't it? Well, go back to quadratics. When I have two factors, right, I factor the quadratic, and I have the product of those two factors equals 0. How do I solve? I've got x minus 3 times x plus 5, all equals 0. How do I get my answers?
You set each of the factors equal.
I set each factor equal 0. And that makes my roots apparent. So if I had x minus 3 as a factor, it means that 3 must be a root. Again, go back to factoring. It all goes back to quadratics. If I have something like this, okay, like that, I would say, well, x equals 3 and x equals -4. Again, that happens when I'm looking at the x-intercept or the root or the solution to the equation. Those are all interchangeable words. And when I have an x-intercept, what's the y-coordinate always? For any x-intercept, what's the y-coordinate? For any x-intercept, what is it?
0.
It's 0. It's 0. Whenever it's an x-intercept, the y-coordinate is 0. So this is like my x-intercept, possibly, if this comes out to be what? 0. When this is 0, it means x minus 3 a factor, which would have made 3 over it. So there's a lot of connections that we're working with here. So let's look at examples that go on beyond this that help us use the remainder to help.
Wait, so the 3 outside becomes the x-coordinate?
Correct.
And so that's what
This is only an x-intercept if this turns out to be what number?
it's 0.
0. So right now, is it an x-intercept? No, it's a coordinate. And the coordinate is right here. 356. Okay? 356 is the coordinate because it didn't work out. In a minute, we'll talk about what happens when it does work out, and we'll look at some examples of that specifically. Okay, specific examples. Let's see. All right. I'm going to go on the next slide here so we can see this. So this is what we're physically talking about here. The factor theorem, there's something called the remainder theorem and a factor theorem. You don't have to really know these words or these names if the operator use them. The factor theorem tells us that the polynomial, whatever it is, has a certain factor if and only if, when you plug c in, it's a root of the equation. Which is exactly what we said when you get a 0 for the remainder. So let's look to see this in example number 2. If x plus 4 is a factor of this, find the other factors. Based on the factors, what are the zeros of the function? All right, not bad. So I'm told already that x plus 4 is a factor. I'm already told, right? So what am I going to do if I plug it in? First of all, what am I plugging into my synthetic table? What number is going to go on the outside if I'm trying to figure out the other factors? Regina, what are we going to use?
-4.
Yeah. And again, I'm going to use -4 out here. And along the top, I'm going to put my coefficients. If it's already stated that x plus 4 is a factor, what is the remainder going to be for short? What will the remainder be for certainty? It has to be. For this to be a factor, what must the remainder be? 0. So I already know that the remainder is going to be 0. So getting to the answer is not the important part. What's important to recognize, if you guys recall, the numbers that show up here turn into my next polynomial that we talked about. So let's do the table just to show that. So let's start by bringing down the 1. Let's go ahead and take the -4 times 1 is -4. -4 plus -5 is -9. That goes right here. Then I take the -4 times -9, and that gives me 36. I take a 36 plus a -22. 36 plus -22 is 14. And then I know the answer, so I don't have to really do this last part, but I'm going to do it anyway to make sure that my numbers are right. -4 times 14 plus +56, 0. So it's really important to recognize that you still need to go through the process, even though you know that 0 is going to be a remainder. 0 will absolutely be a remainder. Start doing what I see Sebastian's already doing. Write down your equation that you get from these three. Think about what the solution should look like. If you started with x cubed and you divide it by x, this should not be x cubed anymore, it should be something else. So write down your next equation from these three parts without the remainder, obviously.
Since there's a factor and the remainder is 0, should you assume that you're already going to have one of the zeros of the function?
Yeah. What is it?
-4.
That's it. -4 is one of the zeros already. Very good. That's exactly right. So if you're told that this is a factor, when you plug it in, you better get 0, right? Because that means that it is indeed a factor. Well, if that's a factor, then this is a remainder. So do we see the corollary here? When something is given as a factor, its opposite in a sense, right? Like we've been seeing all year, becomes the actual 0 of the function, which is proven by a 0 remainder. So remember, this is really the y coordinate. So what do I have on the right? I'm going to write something down. Here's what I'm going to write. I'm going to jot this down. I've got the coordinate -4, 0. And that's one of my roots. Okay, one of my roots is -4, 0. I call it zeros of the function here, so instead of roots, if you want to call it zeros. Okay, that's one of our zeros. But we have how many zeros for this problem? How many do we have? Two?
I know, one.
Look at the original, Alex. Why?
Because the x is
Look at the highest power of the original, x cubed. What does that tell me? I will guarantee you that you will get 3 answers. Now, they might not all be real. They could be imaginary. And if you recall, imaginary roots come in pairs, plus or minus. Remember complex conjugates? 2 plus or minus I, or 3 plus or minus I. They come in pairs. So I already have one of my roots. So the other 2 roots could both be real, they could both be imaginary, or they could be repeated. So I have to go back to quadratics and revisit that in my mind. I need to open up that folder with the discriminant in my mind that told me about the 3 cases, remember? 3 cases for the discriminant. Now, where am I getting at? Well, I'm getting at this. Again, bring this down. I know for a fact that this is also a factor of the original. Why is this quadratic also a factor of the original f of x?
Because the remainder is 0.
Whenever the remainder is 0, the other thing is a factor. If I divide something by one of its factors, I always get the other factor. What's 36 divided by 9? Well, it's 4. Because isn't 9 a factor of 36? So don't you get another factor of 36 as 9, as 4? 9 and 4 are the factors. Well, here, because I know that x plus 4 is one of the factors, whatever I get here as an answer, because this was 0, makes this automatically a factor of the original function. So I know that this times this is really my original function right now. This is the factored form of my original function, isn't it? Okay, look at it. F of x is whatever this is, which is what I started with, times the other factor, which is this. You could go ahead and FOIL this out, or triple distribute, right? Triple distribute. You'll get back to the original if you do it. It's a lot of work, you don't have to do it today, but you will get back to the original. So whenever you get a 0 as a remainder, again, it means that this was one of our zeros of the function, or the roots. And if negative 4 is a root, then x plus 4 must be a factor, because that was stated in the beginning of the problem. If x plus 4 is a factor, this answer you get every time, literally every time, this answer will be the other factor. Now, can you factor this further? Are there 2 numbers that multiply to 14 and add up to negative 9? What are they? What are they?
X minus 7 and x minus 2.
I would agree with Alex. X minus 7, x minus 2. So what are my 3 roots of this problem? Negative 4, 7, and 2. Again, what are my zeros of the function? Negative 4, 7, and 2. Give me your calculator. Go to y1, please. Go to your graph, y1. You should know what I mean by now. If you don't ask me, but you should know what I mean. Okay, y equals. In y1, clear out whatever's there, please. If you don't have your calculator, you can look on. Neither of you have? You know, but you gotta bring your graph calculator, because on the test you use your graph calculator, right? Come on. Do you not have, neither of you have a graph calculator right now? So go up, see Julia, Alex. No, slide over, Laura. No? Slide over. Got it? You take it out. You guys gotta use your graph calculator. We gotta get off the iPads. I know it's convenient. When you're doing homework, it's okay. But even when you're doing homework, practicing with this will make it easier to use this on the test. You can't use this on the test. You cannot use an iPad on the AP exam or SATs. Please carry it around with you. In y1, type the original, please. Type the original function in y1. I say this and you guys think it's like, not a big deal, but I'll tell you now that I have seniors in my engineering class who, because they've never brought the calculator or used it regularly, don't know how to type a function into Y1. They don't know where the X key is on the keyboard because they never practice it. And some of you probably know how to do this because you've used it before, but reiterate it. Please bring it in so that you can practice it more, so that when you're doing it as a whole on your test, it becomes second nature then. So type in the original in Y1 and then exhume 6 so that you get a standardized graph. Type the original in Y1 and then exhume 6. So you're all caught up in the exponent. See that? You gotta get out of there. So get clear, go back to the beginning. Just clear the whole thing. So you go back, slide. Right power. Right. Oh, so right out. Okay. I don't know if it's down there. Right out. So it drops down again. You're on what's called math print. I don't like math print. I use what's called classic, but if you like to see the exponent pop up and stuff like that, you can leave it down there. There's another way to command it. Show. Okay, put on the first. You got it? Check it. There? I have a multimeter over here. You can see which batteries are dead. So you're just going to throw them all out. You just throw one out. If you want to check afterwards, you can look up the multimeter too. Good? Good? Yeah, got the graph? Graph, 2 to 6? You're getting an error. You're getting an error now. Up to these plots. Up. And enter. The next one. You want to turn it off, so you enter. On either of them. And go to the other one, and then enter. Now the graph. Zoom 6 or something.
Did you see that?
It should never be on. I'll show you statistics. Right? Good, good. Good, finishing, good. Missing, show it. Okay. So, syntax here. So hit go to. Go down. Nope.
Oh, sorry.
It's going to happen again. So do it again. Do it again. Your syntax errors in your Y10. Hit go to. See where it brings you? Watch it go all the way down. Clear. Now we're
Thank you.
okay. Guys, if you get an error, this is something I talked about yesterday, Mr. Hall, and students today don't even, you don't see it enough, I guess. When you get an error, there are two options. One says like ignore, and the other one says go to. Always hit go to. It brings you to the error in the syntax that you have to correct. So when you hit go to, it usually takes you to where the mistake was that you typed in that you can then correct. Now you would have gotten an error also if your plots were on and you tried to graph it. So when you'd go to it, it would have brought you right to that plot and you would have to turn that off. Now, look at your x-intercepts. What are they? What are your x-intercepts? Look at it physically. What do you got? Yeah.
They're the same as your zeros.
Yeah, they're the same as these answers here. It's not a coincidence. We just factored this problem or this function to get ourselves 3 factors. 2, 7, and -4 are the zeros. Those are your x-intercepts on your graph. So we're going to be looking at polynomial functions with x to the 3rd, x to the 4th, x to the 5th, and you're going to have to figure out how to find the x-intercepts. This method of synthetic division, where you eventually get a quadratic left over here, is very useful. What if I started with x to the 4th power in the original up top? If I started with x to the 4th, what would this be here, Laura?
That would be x to the 3rd.
Yeah. So if we start with x to the 4th, we might know one factor. It'll break this down and make it x to the 3rd, right? Well, then we have to make another, see this table right here? We'd have to make another table with this as our headings. Imagine this was x cubed. Like 1, 2, 7, 8. That would make another, I call it a subtable. You have to make another table with those headings. Now, in the next lesson, I'm going to teach you guys how to estimate what possible answers might be the roots without looking at your calculator. But for today, and for the next couple prompts, sometimes it's useful to start by graphing it on here. Take a look. Okay, it looks like it crosses at 2. It crosses at 7. It crosses at -4. It could be -4.01 though. I don't know. Maybe it's an irrational answer, right? So I can look at the x-intercepts here and try them. Physically try them in the synthetic table until I get a 0 on the end. So we're going to see that in a little bit, where we're going to try values instead of being given certain values. So let's take a look at number 3 to prove this a little more. It's fine. Yeah. Let's take a look at number 3 here. So you're told that x equals 1 is a root of the equation. So not a function. Not a function. So if I wanted to, I could graph this. I know it doesn't say f of x equals. It says 0 equals. But if I'm looking at this and it says 0 equals, when an equation equals 0, I'm looking for the roots, really. The roots of the x-intercepts. So I could just graph this in y1 and find out what the x-intercepts are in my calculator. But because I know synthetic division now, I don't need to do that. We'll check it on the calculator in a minute. Let's use synthetic division. Across the top, I know what I have. The top is always the easy part. What goes on the outside this time? Yeah, so what goes on the outside here, though? We're not doing long division. What number? It's only a number, right? 1. Okay, so what Helen is pointing out is if the root is x equals 1, what was the factor? If a root is 1, the factor is x minus 1. If a root is 2, the factor is x minus 2. This is all back from second quarter, third quarter stuff. This means that one of the factors must be x minus 1. I don't even care about that. That's not helping me. I'm writing it up here to give you guys little tidbits and notes. But the fact that I'm giving the root right away, I don't have to actually even think about what the factor was. Yeah, the factor is x minus 1, that's great. But x minus 1 is just giving me the root in the end. So I'm kind of going backwards by listing the factor. It doesn't do me any good. What it does help me with, though, is recognizing that if 1 is a root, what's going to come out over here as an answer? If 1 is a root, and this is the x value, what's the y value going to be? 0. So whenever you're told that something's a root, if you plug it in a synthetic table, it's got to be 0 at the end. So let's prove that again. Start by bringing this down. Bring down the 1. Again, we multiply and we add. We multiply and we add. We get 1 plus negative 4 gives me negative 3. Again, we multiply next and we add. 1 times negative 3 is negative 3. Negative 3 and negative 15 is negative 18. One last time. I'm doing this slowly, so if you don't get it, I expect you to look up. If you get it, that's fine. You can be doing it yourself. Okay, but make sure if you don't get this, you're watching. 1 times negative 18 is negative 18. Plus positive 18, well, what's that? Clearly 0. It's not a coincidence. It's not a coincidence. So what this tells me is that one of my roots is 1 comma 0. Did that give me any new information? Is that new to me, that 1, 0 is a point? No. It was told in the beginning. I'm told right off the bat, if x equals 1 is a root. So why am I doing this? Why is this useful at this point? That's a redundancy. I already know that 1 is a root. I was told in the problem that 1 is a root, so x minus 1 is a factor. So when I plug this in, I'm guaranteed to get 0, which gives me the same information. I have no information that's new now. So why do I do this?
You need the other numbers to make the other factor.
This is the other factor. Always take what's left over here when you have a 0 and bring these down as the second factor of the original equation. Again, bring these down always. And this is the second factor. One sec, Mauro. So I know now that this statement is true. X minus 1, which was the first factor, and this messy thing must equal 0. Again, how do I know that? Because this is the same thing right up here. Okay, I'm literally replacing the expression. Take a look up here, please. I'm replacing this 4-term expression right here with its equivalent value down here. Again, x minus 1 is one of the factors. This is the other factor. So this statement is true, and if this statement is true, I know that this will give me one of the roots, and the factors of these will help me to find the others. So go ahead and factor this. Question, shoot.
How do you know that minus 1's a factor.
Because x equals 1 was a root. Remember how roots come from factors?
Yeah.
Think about the quadratic. How do I get the factor? What is the factor? This is x minus 1, right? So here, if I look at this part, I set this equal to 0. T-chart, remember? Set this equal to 0. What do you get as an answer? X equals 1, right? So when you get x equals 1 as a root, if you're told that, you know that that's going to be a factor automatically. They are related to each other. The factor and the root kind of have opposing values when you think of it that way. So what do I get when I factor x squared minus 3x minus 18?
X minus 6 and x plus 3.
Agree? Disagree? I think it sounds right. Right? That sounds good to me factor-wise. So what are my overall roots for this then, automatically?
1, 6, and -3.
Okay? So given one of the factors, like in the last example, we can find the other factors. Given one of the roots, as in this example, I can find the other roots. This is very useful for cubic equations. Notice this was cubic, the original, was for the third power. The minute I get to the fourth power, I have to be given two roots to do this process twice. We're going to see more of that in the next class. So for today, not to get too much ahead of myself, because I do that sometimes, I'm going to stick with just this for now, with cubic only. We'll get to quartic and fourth power and fifth power in the next lesson. Okay, let's take a look at one more example here. A little bit different here. A little bit different. Don't do the work. Just talk to me about it. Determine if x plus 2 is a factor of the following polynomials. How do I know if something is a factor or not?
You plug it in, and if there's a remainder, then it's not a factor.
Awesome job. Well done. When the remainder is 0, it's a factor. We said that before. So Eduardo just said the corollary to that, right? Or the converse to that, really. He said, you know what? If I plug it into the table and I don't get 0, it's not a factor. Absolutely right. Very good. Well done. Okay, that's a little bit tricky here. We have to consider the fact that we have to work backwards too with these. So if I plug in, though, what goes on the outside? If I'm testing x plus 2 as a factor, negative 2 goes on the outside. And then along the top, I just simply list the values. Bring down the 2. Negative 2 times positive 2 is negative 4. Negative 4 plus negative 4 is negative 8. Next. Negative 2 times negative 8 is 16. 16 plus 1 is 17. And then finally, negative 2 times 17 is negative 34. Is it going to work? So can I just stop there at this point? Yeah. I'm not getting 0. I don't even care about what this number is. I'll do it. Negative 34 and 7 is going to be negative 27. But because the remainder does not equal 0, x plus 2 is not equal to a factor. That's what Eduardo told us a minute ago. So can I make a subtable from this? Can I take these three coefficients and now make a quadratic and find more factors at this point? Absolutely not. Because I can't do that because this one isn't a factor this time. Anytime that I get 0 here, it means that this one was a factor, and as a result, what remains is also a factor. But if I test x plus 2 and prove that it's not a factor, it means that 2x squared minus 8x plus 17 is also not a factor. So the key in this lesson is to recognize that when you get 0 as a remainder, that's when you're golden, right? Prior to that, if you get any other number besides 0 as a remainder, you're pretty much told it's not a factor or not a root. That's what you know from this. So 0 as the remainder is the key to this lesson. Anytime 0 is a remainder, it means that that is a factor, and therefore, whatever number you're testing is a root. Is a root on the outside. That's the whole gist of this entire lesson. There are some other quick things I want to point out on this slide. This is stuff that I've actually already talked about. Alex helped us out with the first one. So the first one earlier, he said, oh, there's 3 roots because it was x to the third, right? Or there are 3 zeros of the function because it was x to the third. That's what the first thing says. Every polynomial equation with a positive degree n being any number, 7, 8, 9, will have that many roots. So if I have x to the 7th, I'm going to get 7 roots. If I have x to the 5th, I'm going to get 5 roots, etc., etc. Some of those roots might be imaginary. And we're going to do examples of that. And tonight with your homework, that trinomial, let me go back real quick. I'm going to pause. The second part, you guys know this already. Is that polynomials that have imaginary roots come in pairs. So if one of the roots is 2 plus 7i, what must the other root be? If the first root is 2 plus 7i, the second root must be 2 minus 7i. A very useful theorem to know. Okay, we've got over both these already this year, but I would maybe jot them down. Okay? You definitely have homework tonight in this section. If you felt like you were a little confused with the last section, hopefully this helped to clear it up a little bit because the process is the same. Okay, the process is the same. Let me try and think for a second. So I'm going to give you a quiz tomorrow. Tomorrow. Thursday? No,
Wednesday.
Tomorrow's at 8. It is. Perfect. I'm going to give you a quiz tomorrow, and then we're going to do 8-7. And then Thursday your problem set is due. And then Friday 8-7 homework is going to be due. You don't have any for class. We'll submit that electronically for everybody. And then Monday is your test. Okay, so keep in mind your test is coming sooner than you think. Test is on Monday. Check your email. They made that test change meeting because Thursday we only have 37-minute periods. That's why we're going to review on Thursday instead.
I have a question. Oh wait, no, it's the problem set. I was gonna ask if the problem set due like Monday and later on Friday, but then there isn't a class set.
Yeah, so what I'm going to do is I'm going to have the problem set due on Thursday when we review like normal. And then that last homework assignment, 8-7, instead of having a double homework, because you're going to be finishing the problem set anyway, you do that the next day. Okay? Please come see me if you're struggling with this, especially if you can see me before tomorrow. Because tomorrow we're doing 8-7, which puts all this together. So if you find that you're still a little bit confused and want a little bit of help in this area, maybe you come by for like 10 minutes after school. I can definitely give you a little time after school today, because baseball will be on campus today. If you need like 10 or 15 minutes, I don't allot that much time after school. You guys want to get lunch early? You have lunch, right?
Yes.
Good. Okay. Have a good rest of the day, guys.